So tonight we're going to go over the last set of topics that's in sections or chapters 1 through 5, section 2. There's about 19 more topics we're going to do. So this means after today I've basically done almost all the topics in the chapters 1 through 5 section, except for some at the very beginning that most people had mastered originally. So you should have section or chapters 1 through 5 done by Sunday. On Monday at midnight, the chapter 6 will unlock. So even if you are not done with chapters 1 through 5, chapter 6 will unlock. However, what will happen if you have a bunch of topics left in chapters 1 through 5 is not all the topics are going to be open to you in chapter 6. So there will be some topics that are locked by things that are in chapters 1 through 5. So you'll have to go back and fill those topics in before you can do some of the trigonometry ones, especially some of the stuff with the not really a lot of the log stuff, but some of the quadratic stuff and things like that, because you have to be able to simplify the fact problems or factoring and stuff like that. That comes up in the trigonometry section. So next week on Wednesday is going to be the test day. So you have to have your test done by midnight on the 23rd. We will not have class next Wednesday, actual class. So if you want to do your test next Wednesday, that's fine. I'll be able to schedule them that way. If you want to do it before that point, just let me know and we'll schedule a time ahead of time. On Monday during class, I'm going to review the test. So we'll go over all the questions that are on the test and how to do them. So if you're looking at the review test and you're struggling with some of the questions, that's going to be your best help for the actual test. So we'll do that on Monday, and then you have to have the test done by Wednesday night, the 23rd. All right, so the first thing we're going to look at, there's 3 or so topics left on graphing of logarithms because we didn't do those. I moved them to this lesson from Monday's class. So when the first topic is just called translating a graph. So it's basically you're going to move the graph. So you don't even have to actually do any real math for it. You're just looking at the problem pieces and translating it. This is what a logarithmic graph will look like. If you notice, it's very similar to an exponential. It's just flipped. So remember, logarithms and exponentials are inverses of each other. So the logarithm is basically the range of the exponential function, and then the domain is the range of the logarithmic function. So it kind of switches over. But the transformation rules still stay the same. If it's inside with the x, I'm going to do the opposite, and I'm going to move it left and right. So for this one, I'm going to move it 4 to the right. Or to the left, sorry. I get my lefts and rights mixed up sometimes. So I'm going to move it 4 to the left. And then I'm going to go down 3 because it's negative 3. So 1, 2, 3. And that's my new equation. So this one is just going to be those type of problems. You're going to have the thing inside, move it left to right, and then the outside, you're going to move it up or down. Let's do one more of those. So this one's got negative 3 inside, so I'm going to move it positive 3. So 1, 2, 3. And then I'm going to go down 2 because of the negative 2 on the outside. If it was a positive 2 on the outside, I'd have gone up 2. All right, the next 2 topics, or the next 2 ones, we actually have to graph them out ourselves. So we need some points. So the key piece when you're graphing these functions is the base number right here. That's the key piece of information, and that kind of obscures what I just is there. So log 3 of x. That's the key piece of information, because that's basically what we're looking at when we're doing the conversion between logarithms and exponential. So remember, if this was y, it'd be 3 to the y equals x. So when we're looking at coming up with points, it's actually the opposite of the way we're doing the exponentials. So in exponentials, we only need 2 points. So if we did 0 and 1, and notice I'm putting them in the y because I'm switching it. So if I do 0 and 1, the x is 1, and then that one's going to be 3 because I'm plugging into there. So 3 to the 0 power is 1. 3 to the first power is 3. So those are the 2 points that I'm going to graph. Now we look at any kind of transformation to it. I've got a +1 on the outside. So that means I'm adding 1 to the y's. So when I do that, this is going to become 1 and 2. So my new points that I'm going to graph when I'm graphing this one is 1, 1, and 3, 2. Now, your asymptote is going to be based on whatever's inside with the x. So, and it's going to be vertical asymptote. So in this case, there's nothing with the x. So my vertical asymptote is going to be on the 0 or on the y-axis. And then I hit graph. I get my nice little curve. Any questions with that? Does the table make sense when we did the x and y? We just did it backwards from what we would normally have done. All right, let's do one more of these. And then we'll do a more complicated one. So this one is log 2. So I'm going to do my xy. Same thing, 0 and 1, but this one's going to be 1 and 2 because it's 2 to the y equals x. Now this time I've got a 3 on the outside, so I'm going to take my y's and multiply by 3. So that stays 0, and that goes to 3. So I do the same thing. Graph those 2 points, and actually I'm just going to graph them with the pen this time. So 1, 0, and 2, 3. My asymptote is still going to be on the y-axis because there's nothing next to the x, and I hit the graph. All right, let's go to a more complicated one. All right, same thing here. I believe you need 2 points. Yep. So you're going to use the same setup for this one that we just did in the last one, except it's one tool to actually click the points instead of having to do multiple ones. So same thing. This one's log 3. So I'm going to do 3 to the y equals x. So my table 0, 1, 1, 3. Now this one has a -3 in the x. So that means I'm going to do x plus 3. So that becomes 4, and that becomes a 6. So remember, you always do the opposite of what it says in the problem. The other thing is when I'm looking at my asymptote, it's going to be at +3. So that's my asymptote. My first point is at 4, 0. And my next point was at 6, 1. Now, your domain is your x. So if you notice, my domain starts at that asymptote. It doesn't go past that one. So my domain is going to be from 3 to infinity. And my range is going to be all real numbers. So just like in the exponential function, I said that the domain was always all real numbers. In a logarithmic function, the range is always all real numbers. Because again, we just switch them basically because they're inverses of each other. And the domain's got my restrictions in it. So in this case, my domain is 3 to infinity because I'm starting at that asymptote line. Let's do one more of those. All right, good. This one's got a couple transformations in it. So same thing. We're going to do, in this case, 4 to the y equals x. So my table is 0, 1, 1, and 4. Now my transformations, I've got 2. So I've got x minus 1. That's going to become 0 and 3. And then I've got y plus 2 on this side. So that becomes 2 and 3. So we have both transformations in this one. So we graph it. My asymptote is going to be at -1 because it's the opposite of what's inside there. And then my 2 points, 0, 2, and 3, 3. The other thing you'll notice is a lot of times if you try to do your asymptote at the 1, if you did your points correctly, you're going to realize that your points are on the other side of it, and it doesn't make any sense. So that's a quick way to realize that you're putting the asymptote on the wrong side of the graph. Like if I tried to put the asymptote at 1 over here, I have a point at 0, 2, which would be on this side, and I have 1 on this side. So we know that can't be true. Now, our domain starts off at my asymptote. So in this case, my domain starts off at -1. It goes to infinity, and my range again is all real numbers, so -infinity to infinity. Any questions with graphing of logarithms? Because this is really the end of graphing of logarithms. Before we go on to actually looking at solving logarithms. All right. All right. Solving logarithms. The first one, when we're looking at just a simple one like this, is you're just going to change it to an exponential function and solve it that way. So for this one, I've got one second. For this one, I've got 5 to the -3rd power equals x. Because remember, this becomes the exponent. So the log 5x equals -3. This becomes my exponent, goes over to there. And then that's the base. So what's 5 to the -3rd power? Well, it's going to be a fraction. So it's going to be 1 over. And then 5 to the 3rd power is 125. So the answer to this problem is 1 over 125. Very good. All right, let's try one more of these real quick. Oh, good. So this one, when I rewrite it, I'm going to get 36 to the 1/2 power equals x. Now, remember, a fractional exponent means a root. So this means the square root of 36, which in this case would be 6. If it was another fraction, so say it was 8 to the 1/3 power, that's the cubed root of 8, which would be 2. So just keep that in mind. Any kind of fractional exponent is a root. So in this case, my answer is 6. All right. All right. Any questions on that one before we move into the actual harder ones where we're actually going to start solving exponent, or we're going to start doing some of the properties of logarithms? All right. Okay. There's a lot of people that ask me when I do this topic in person. It's like, why are we doing this when a calculator can do most of this work for us? You're absolutely right. And actually, the only reason we do this now is so when we work with equations, we can start to be able to manipulate equations. So originally, when logarithms were done, you actually didn't have a calculator. So they actually had to solve it based on a book. So what we did was we took our logarithms and we broke them down all into prime numbers. Oh, somebody had a question?
Yes, Keegan did. So how do you go about solving an exponential equation where the exponent is a fraction other than like 1/2, 1/3? Like what if it's 5/3?
So you do the third first. Well, actually, you could do it either way. So normally I would do the root first. So I can do one real quick for you. Let's do. I'm going to do an easy one. So let's do 8. Actually, do 8. That's what I wanted. Let's do 8 to the 5/3. So you do it in two parts. So you do the third root of 8, and then you raise that answer to the 5th power. So in this case, that would be 2 to the 5th power. So the answer is 32.
Thank you very much. That makes a lot of sense now.
All right. So we used to break them down into prime numbers. So that's why we have to go through and do all these wonderful little rules. If you remember your exponent rules, the logarithm rules are basically the inverse of them. So in an exponent rule, if we had multiplication, you would add the exponents. If you had division, you would subtract the exponents. So it's a minus b. So the same rules apply in logarithms, though they're reversed. So this first, the logarithm rule. So if we have log a of whatever it is of x minus log a of y, the subtraction is division. So that's the same thing as saying log a of x over y. Addition is the same thing. So if we do log a of x plus log a of y, then we would multiply. So it's log a of x times y. So when we're looking, the key piece is the base number has to be the same. So the base number is just like those two x's. If the base number is not the same, I can't put them together. So in this one, I got log 4 of the 5th, or base 4 of 5 minus log base 4 of 9. So I'm going to divide those. So that's 5 divided by 9. This one, I have log base 5 of 8 plus log base 5 of something equals log base 5 of 24. So what number am I going to multiply the 8 by to get 24? In that case, it's 3. The number out in front is an exponent. So the log, so if I have log a of x to the m power, that m actually can come down in front. So that becomes a to the x. So when I'm looking at this problem, I have a 9 here, and now it becomes a 3. So 3 to what power would give you 9? In this case, as Caleb just put in chat, very good, it is 2. All right, so let's try one more of those. So addition. So I'm going to do 3 plus the 5. So in this case, with logs, I'm going to multiply. So 3 times 5 is 15. This one's division. So it's 5 over 4. So this one becomes really easy because the number's already there. 5 over 4. 5 and then 4. Now, this one, they're giving you the exponent. Hold on 1 second. Sorry, dog was loud. All right, so they gave me the exponent of this one. So I need to figure out what raised to the third power is going to give you 27, which in this case, very good, is 3. Now, when we're doing numbers, it's pretty simple. We're going to have to start solving some equations in a little bit, and that's where we're going to actually really need to know those rules. All right, so now this one, they want us to use the properties of logarithms to expand it out. And they want us to expand it out so that there's no exponents and there's no multiplication or division. So I've got log. And if there's no base, you don't have to worry about it. It's considered automatically base 10. So then I've got z over y to the 8th power. So the first thing I'm going to do is let's get rid of that division. So this becomes, since it's division, it's log z minus log y to the 8th. And then I'm going to get rid of my exponent by moving it down in front. So it's log z minus 8 log y. And the rules stay the same no matter what the bases are. So base 10, base E. So if it's just ln, all the rules still stay the same. Nothing's going to change. So they've got the button. So log z minus 8 log y. You can't have different bases when you're breaking them up. They got to be the same bases. So these are all base 10. And the ones we were looking at before, most of them actually were base 4. But they just have to be the same base in the same problem. So like this one couldn't be base 10 and this one be base 5. It wouldn't work that way. Yeah, let's try one more of these. So this one is multiplication. So I've got log y squared and then z. So multiplication is addition. So it's log y squared plus log of z. And then that exponent comes down in front. So I've got log y plus log z. All right, next topic, we're actually going to put them back together. So just like we were expanding them out, when you're putting them back together, we have to work our way across. So we've got the 1/5 log 5 of x plus 2 log 5 of w minus log 5 of y. So we're going to put the exponents back up first. So it's log 5 of x to the 1/5 plus log 5 of w squared minus log 5 of y. And now we're going to put together the first two are addition, so that's going to be multiplication, and then it's going to be divided by the y. So it's log 5 of x to the 1/5 times w to the second over y. So log base 5, and then we have to put in x to the 1/5 w. All right, let's do that. X, really? W squared, and then y down the bottom, and I got to get rid of that x in front. So you're basically just combining and putting the stuff back together there. All right. Next one, another one is the change of base formula, which if you have an older calculator, you still have to do. The newer calculators will do it for you. So the change of base formula allows me basically to change anything, any base into any other base I want. Typically, your calculators had base 10 on it or ln. So you can do either one of those. So log 5 to the 3 becomes log 3 over log 5. So the formula is log base of x equals log x over log base. And you also could do ln of x over ln of b. So the change of base formula allows you to change it into any base you want. So typically we use base 10 or base e, which is the ln, but it doesn't make much difference. They're all going to come out to be the same answer. So if we use the calculator, so if we did log 3 divided by log 5, we get the answer as 0.68, and we're rounding to 3 decimal places, so it's 683. Now, if I did, just to show you, if I did ln of 3 divided by ln of 5, it comes out to be the exact same answer. So it doesn't make a difference which base you turn it into. And this calculator doesn't give me the ability to do different bases, but even if you did base 2 of 3 over log 2 base 2 of 5, it still would come out to be the exact same answer. Again, a relic of the past times when we actually had to use books or tables and archaic calculators. All right, solving logarithmic equations. So an inverse function allows me to get rid of something. So just like if we're looking at addition and subtraction, those are inverse functions. So if we add something and then subtract it, we're back to where we started. Logarithms and exponentials are also inverse functions of each other. So to do this problem, I've got log base 3 of negative 4x plus 10 equals 3. I'm going to take the base, which in this case is 3, and raise both sides to the third power. So what I'm left with is this part over here cancels itself out, and I'm left with just the negative 4x plus 10. This side, I get 3 to the third power, which is 27. Now I got a simple equation to solve. Minus 10, so negative 4x equals 17. So x equals negative 17 over 4. Good habit to get into. This topic won't ever have this problem, but other ones that we're going to do in a few minutes will. You want to plug the value you get back into the log. So we're going to take that and we're going to plug it back in. So I've got negative 4 times negative 17 over 4 plus 10. So this is going to be 17 plus 10, which is 27. So I'll answer the second question 1 second, Caleb. So the reason we want to plug it back in is because inside of a logarithm, you can never have a negative number. So since I've got the positive 27, I know this answer is going to work. So this one's going to be negative 17 over 4. Now, yes, Caleb. So we're going to cancel log base 3 by raising them both to the third power. So if it was log base 5, I would have raised them both to the fifth. I would have raised it to the fifth, or not to the fifth power. I'd have put the whole thing with a 5 as the base. So you're really not raising it to the third power. You're actually making the base the third, and the stuff is going up in the exponent. So I wish those numbers at the end weren't the same. And hopefully the next one, they're not going to be the same, because it'll make it a little more sense. Good. All right, so let's do this one real quick, and I'll since it's a different number, I think it'll make it a little clearer. So log 5 2x minus 4 equals 2. So I'm going to put 5 as my base on both sides. So this piece over here is gone. And I'm left with 2x minus 4. This side is 5 to the second power, which is 25. So remember, the power isn't 5, the base is 5. So then we add the 4. So we get 2x equals 29. So x equals 29 over 2. And if I look at that one, I can just look at it and know that 29 over 2 is definitely going to make this still positive. So I don't really have to plug it back in to try it. It's going to be 29 minus 4, which is 25. So 29 divided by 2 is the answer there. All right. The same rules apply if I have an exponential function and I want to move it to a logarithmic function. So in this case, I've got e to the 6y equals 12. I want to get that part down. So what I'm going to do is I'm actually going to do the ln of both sides, because the ln and the e is going to cancel each other out. And then I'm left with 6y equals ln of 12. And then divide by 6. So y equals ln of 12 over 6, which we're going to have to use the calculator to figure out. So we do ln of 12 divided by 6. Now, it's not ln of 2. That 6 is not dividing the 12. It's dividing the function of ln of 12. So you will get two different answers if you do ln of 2 in this. So it's 0. And we're doing hundredths, so 0.41 in this one. Let's do one more of those. So this one, we've got e to the y plus 5 equals 15. Same thing, I'm going to do the ln of both sides. So I get y plus 5 equals ln of 15. So I'm going to subtract 5 from both sides. So y equals -5 plus ln of 15. There is a reason I didn't write ln of 15 minus 5, because what happens is it's really easy to think, well, the 15 and the 5 go together. So by putting the ln at the end, I don't have that problem of worrying about it. So in this case, I'm going to do -5 plus ln of 15. Then we get -2.29. What you don't want to do is you don't want to do the ln of 15 first. Get that answer, round it, and then -5. Like I can do -5 right from there and I'll still get the same answer. But if you then have to take that number and type it back in, so it's like, oh, well, that's 2.71. And then I type in the -5, I might not get the exact same answer because you're losing information. So just be very careful when you're doing it. Just type the whole thing right in the calculator. Your cell phone calculator may or may not be able to do it, but the ALEKS calculator can, and Desmos can as well. So using those two options is probably your best bet. All right. Let's keep working on solving. So now notice the key pieces, no matter what the function is, the concept for logs is the same. So in this case, I've got 5 plus 2 ln x equals 3. So the first thing I have to do before I can worry to do the ln's is I got to get everything away from the other from that ln. I can't raise this to a power or deal with or put it into the power without having to get the ln by itself. So I have to subtract the 5 first. So I got 2 ln of x equals -2. I divide by the 2. So I get ln of x equals -1. And now I'm going to raise both sides with e on the bottom. So that's going to cancel out. So x equals e to the -1st power. Hold on one second. So sorry about that. So in the calculator, we're going to do e to the -1st power, which was 0.3 and then 100, so 7. All right, moving along, solving more complicated problems. All right, so the next one's got logs on both sides of the equation. We're actually going to do the exact same thing. So when you have a log on both sides, we need to get the logs on one side before we do the actual problem. So, because we basically have to get this to be one log before I can solve it. So I've got log 4 x minus 6 equals 1 minus log 4 x minus 3. If the 1 wasn't there, if this 1 minus wasn't there, I would have just been able to put 4 under both of them and cancel them both out. But since that 1's there, I can't do that. So I've got to bring the log over to the other side. So I got log 4 of x minus 6 plus log 4 of x minus 3 equals 1. Now, I need to put these together, so I only have one log. Remember, addition is multiplication. So I have log 4 of x minus 6 times x minus 3 equals 1. Now, I can bring everything up to the 4, raise it, and put it in the exponent. And I'm going to use 4 to do it. So this side is going to be, and I'm going to FOIL this out because we're going to have to bring over the 4. So I get x squared minus 9x plus 18 equals 4. Bring the 4 over. So plus 14 equals 0. And now we can factor again. So I've got x minus 7 and x minus 2. So my two answers are x equals 7 and x equals 2. We now have to try both of those answers in the problem. So remember what I was saying before and why we checked one of the first ones was we have to make sure that they do not come out to be a negative number. So if I plug the 7 into the x minus 6, that's a 1. If I plug the 7 into x minus 3, that's 4. So 7 I know works. If I plug 2 in, 2 minus 6 is -4. So the 2 does not work. It is not always going to be the case that 1 works. You could have 1 that works, you could have both of them that works, you could have neither one that works. So you do have to check them all. So if none of them worked, that's where the no solution button comes into play. So you would just click that. So the only number that works out of this one is 7. All right. The next topic's the same one that's just a little more complicated. So we're going to go on to the next one. Because there's a problem type 1 and a problem type 2. All right. So this one, same thing. We're going to try to put the stuff together so there's one log. In this case, there's nothing actually extra, so there's just going to be one log on both sides. So we have log x minus 5 minus log of 17. So this one's going to become my division. So I've got log of 19 equals log of x minus 5 over 17. Now, since I have one log on both sides, I can just raise them both to the 10th power, and they will cancel out. So I have 19 equals x minus 5 over 17. So now we multiply quickly. What's 19 times 17? So I don't have to grab my calculator. Oh, come on. We got all the easy ones, but now I ask you to multiply one, and we can't come up with it that quick. There we go. 323. And then we add the 5. So we get 328 is x. Now, if I plug 328 into that, obviously it's going to be positive. So the answer is 328. All right, let me try one more because that one actually wasn't. This one, I guess, is all basically the same. So ln, no difference. I would just use e to get rid of it. So we're going to go on from this. All right. All the rest of the problems we're going to look at is word problems. So any other questions on solving logarithms? All right. Moving on to the wonderful word problems. Okay. When you're looking at exponential growth problems, the function is p, and then it's 1 plus r to the t power. So this problem, we've got 330,000. And we got 1 plus, it's growing by 9%, so it's 0.09. If it was decreasing by 9%, I would have just changed that to a minus, and we want it after 13 years. Just write the equation and then go to the calculator, and you can type the entire thing right into the calculator. So in this, we're going to do the 33. Make sure you have all the zeros. 1 plus 0.09 raised to the 13th power. Now we can't have half a person, so we want to round to the nearest whole number. So it's 1011716. You do not have to put commas, as I showed. They like commas, but you do not have to put commas between your numbers. Now, this word problem, they're actually giving you the equation, but they want other information out of it. So Tom wants to drink water when it reaches a temperature of 13 degrees Celsius. How many minutes should he leave it in the cooler? So this time we're not looking for the answer, we're actually looking for t. So we have to do a little bit of calculations and with using the logarithms to figure this one out. So they want 13. So it's going to be 13 equals 5 plus 13 e to the negative 0.04 t. So subtract the 5. Divide by the 13. And since it's base e, we're going to use ln's. So it's ln of 8/13 equals negative 0.04 t. So that we divide with the negative 0.04. And that's going to give me my t. So again, we're going to type that entire thing right in the calculator in one shot. So ln 8/13 by 0.04. And they want it rounded to the nearest tenth. So in this case, it's 12.1 minutes. Nice thing about this topic is they're always going to give you the equation, so you don't have to figure it out. And a lot of times on this one, it's going to be using with ease, so you're just going to use the ln to get rid of it. Any questions on this one? Yeah, this is a continuous growth model. Or a continuous decay model, depending on the direction it's going. Something you don't want interest if you're having to pay it. So yeah, the other one is just the other one's a growth model. It's just not continuous. It's based on once per period. So basically, if you're looking at compounding, which we talked about when we are doing interest, you have compounding annually, semi-annually, monthly, daily. You can keep going. E is continuous. Like it's always putting it into it. So all I did was actually just typed it right in the calculator. Type that back in. So I typed in the answer, the ln 8/13 divided by the negative 0.04. Yeah, I'll do one more of them. So that was 12.1. All right, let's do one more of these. All right, so this one is a drugs in a bloodstream. So we want to know, so when the milligrams reaches 9, then we need more of the drug to be re-injected. So my answer is going to be 9. So it's 9 equals 20 e to the negative 0.45 h. So we divide by 20. So if you ever, it's one of those really cool things. So most people, if you get your drugs from the doctor, antibiotics or anything else like that, your doctor gives you very specific directions on when to take it. You're supposed to take it every 8 hours or every 12 hours or once a day at the same time. The reason for that is that the drug goes into your system and decays over time. So when you retake the next dose, it jumps you back up, but the previous dose is not completely out of your system. So it actually goes above what the dosage on the pill is in your system. The doctors know this when they prescribe it, or other companies have actually done it, and it's in the literature. So the dosage that you're actually getting that actually is going to solve your problem isn't actually the milligrams on the pill. It's actually what's going to be in your bloodstream at the time. So if you don't take it when they prescribe it and on the times that they prescribe it, it actually would drop below it and it will not be as effective as it needs to be. So like this one, this is an automatic type thing. So once it hits 9, it's going to automatically give it to you, kind of like in the hospital. So just little things to how medicine works. So this one we're going to do the ln of them. So we got ln of 9 over 20 equals the negative 0.45h. Then we're going to divide by the negative 0.45. So we go to the calculator. And we type in, we'll put the division in first. ln 9 over 20, and then negative 0.45. So we wanted to round this to the nearest tenth. So it's 1.8 hours. So every 1.8 hours, the drug needs to be injected to keep it at or above 9 milligrams. All right, let's do the next one. Okay, so it says the continuous exponential growth model. So I like to call the continuous exponential growth model the PERT model, if anybody remembers that shampoo from way back when, because the equation is really A equals P E R T. That's where PERT comes from. So it's very similar to what we were doing before with the other function, except that it's the E and the rates in the multiplication part there. So a number of bacteria in a certain population increases according to this, with a growth parameter of 4.9% per hour. How many hours does it take the sample size to double? Notice it doesn't tell you how big the sample size was originally. You can do this one of two ways. You can do it with a variable, or you can just pick any number you want and double it. So I'm actually just going to pick any number I want. So we're going to start off with 100. And then it's e to the 0.049 t. And doubling it would mean there was 200 of them left. So when I divide it, it's 2 equals e to the 0.049. We do the ln of both sides, so it's ln of 2. 0.049 t, and then we divide by the 0.049. So notice it didn't matter which numbers I pick, it was always going to come out to be 2 there. That's why I said you could do it with variables, just to like an x and a 2x. It would have still come out to be the same way. I just like picking the numbers. It just makes it a little bit easier to see and read. So we're going to go and put it in to the calculator. So we've got ln of 2 divided by 0.049. So in this case, it's running the nearest hundredth. So it's 14.15. And if it said triple, I would have tripled it. If it said the half-life, you'd cut it in half. So it would have been 150. Same concept, same process. All right, so this one, if you think about it, it's no different than the last problem we just did. They wanted to know after how many years will the initial investment double? So they gave me the equation, which is just a continuous growth equation. Although I don't know if this topic has them all being continuous growth or not. No, this one's not always continuous. Well, actually, it's half-life and doubling, so most likely it is. So it's doubling in this one. So that means I could do the 200 and the 100 again, or I just know it's going to be 2 equals e to the 0.035 t. So then I do ln of 2, 0.035 of t and divide by the 0.035. So it's the exact same thing we just did in the last problem. They just gave me the equation for this one instead of having to come up with it. We'll do one more of these because there's a half-life one in here too. So ln of 2 divided by 0.035. And they went to the nearest tenth, so it's 19.8 years. Try one more. I want to see if we can get the half-life one. Oh. There we go. All right, so this one is talking about half-life. If any of you are doing anything with radioactivity or chemistry and stuff like that, you deal with half-lives. So the only difference in this one is that y is going to be 1/2. So I'm going to have 1/2 equals e to the negative 0.062 t. So then I do ln of 1/2 equals negative 0.062 t. Let me divide by the negative 0.062. So there's nothing different if it's a doubling or a half-life. It's just the number at the end is what changes. So it's either going to be a 2 or a 1/2. Calculator is the same process. And then negative 0.062. So this one gets cut in half, 1 decimal place, so 11.2 days. Any questions with these? Next ones we're actually have to write the equations. So all right, 2 more to go. All right, so this topic, you have to write the equation and then come up with an answer from it. So it says a radioactive substance has an initial mass of 451.7 milligrams. It's a continuous exponential decay model, and it has a half-life of 8 days. So the initial point is the 541.7. When you do the part up here, we have to do the calculation for it. So we know that it's going to cut in half. So we know that it's going to cut in half. So 1/2 equals E, and it's the 8x. So we're trying to solve for that x up there. So it's ln of 1/2 equals, I think it's just not writing correctly today, 8x. So then we're going to divide by the 8. So we go to the calculator. So we have ln of 1/2 divided by 8. So you actually can put in the whole thing. So actually we're just going to do 1/2. So ln 2/8. So now we're going to type this in, but time is going to be 14 days. So we do 451.7 e to the ln 1 divided by 2 divided by 8. All right, let's try that one again. 2. And then times 14. So then after 14 days, we have 134.3 milligrams. So they don't want you to actually do the approximations. They want the exact thing in there. So you don't want to come up with the decimal. You actually want to type that whole thing in there. Notice in this part, though, I didn't use the 451.7 because it didn't matter. I was just looking for the half-life, which was set to a half. And the 8 days came from there. They told me the half-life was 8 days. So, all right, let's do one more of those. Now this one's looking at doubling time. So the initial presence is 4.4, so that one I can type in there. And then we're looking at doubling. So 2 equals E, and it says it doubles every 15 minutes. So 15x. So it's ln of 2 equals 15x. So it's ln of 2 divided by 15. So if you think about it, when you're actually going through and doing them, so you don't even really have to write it out once you look at a couple of them. It's going to be ln of if it's doubling 2, if it's a half, half. And it's always going to be divided by whatever the doubling time was or the half-life time was. So we've got division ln of 2 over 15, because the other one was ln of 1/2 over 8. And then we want to know what happens after 14 minutes. So we're going to plug that equation in. So 4.4 e raised to the ln of 2 divided by 15. And then times 14. So we have there's 10, so it's 8.4 milligrams. All right, one more to go. All right, so it says there's a sample of 600 milligrams radioactive substance. Since then, the sample has decayed by 4.1% each year. Let T be the number of years since the start of the study. So this one goes back to the equation we were doing before. So it's A equals P 1 plus R to the T. So this one's going to be 600. 1, and it's decaying by 4.1% per year, so it's minus 0.041 T. And the sample size is Y. Now we'll see if they actually let me put it in there with the subtraction. If not, we just have to subtract it, which isn't a problem. Raised to the T. Yeah, so they say you can write it that way. So you can leave it like this, or you can actually break it down. It doesn't make much difference in the answer. right, let's try one more. I just want to see if they actually do one with an exponential growth or with the e. Nope, it's the same setup. So y equals the original amount. And then this is growth, so it's 1 plus 0.59. And it's raised to the t years. Oh, I missed the 0. That's it. So that's the end topics in chapters 1 through 5. So. All right. I'm going to stop the recording. If you have any questions or anything else, you can stick around and ask the questions. If not, we're done. You can go work on topics. Remember, you want to get chapters 1 through 5 as most done as you possibly can by Sunday night. And then we'll do the test next week. If you're done earlier and you want to do the test, just let me know.